Right. Hello, everybody. Welcome to Objective 1 of our Algebra B review. Okay, today we're talking about solving systems of equations. Now, first off, what is a system of equations? Well, let's give you a real-world example where you'd want to use something like this. Okay, let's talk about hybrid vehicles. Okay, let's say that a Ford Escape sells for $26,000 and on average costs 10 cents per mile to drive. Again, the Ford Escape Hybrid, so the same car but the hybrid model, costs $28,000 and average costs 8 cents per mile to drive. Okay, typically when you're thinking hybrid electric vehicles, the cost up front is greater. Okay, those type of vehicles have more technology in them. They cost more to buy. Okay, but the trade-off is each mile you drive as you're using battery power as opposed to gasoline, you're going to save some money per mile. So the big question is how many miles would I need to drive to make this worth it? Okay, does my driving style, justify buying a hybrid vehicle? Okay, so how could we approach a problem like this? Well, it'd be pretty simple to come up with a formula for the cost of both these vehicles. Okay, for the, let's call it a normal car, we'd say the cost is equal to the initial cost, $26,000. Okay, and then plus 10 cents per mile, so we'll say 0.10 M. And then for the hybrid, same idea. Its cost is going to be equal to the initial cost of $28,000 plus 8 cents per mile. Now the question is I have two different equations, and since both equations have two variables in them, I can't actually solve them for one variable. I can't solve it for mile or I can't solve it for cost. The trick with a problem like this is looking at both equations combined. That's my idea of a system of equations. More than one equation with more than one variable, and what I can do is I can look at some different methods, and what we'll do today is look at different methods of combining these two equations to come up with a solution. Alright, so just giving you the definitions of what we just talked about. So we're talking about systems of linear equations here, and that's just two or more linear equations. And then a solution of a system of linear equations is just any ordered pair, x and y values, okay, or we could think of c and m like we just looked at, that make all the equations true. Okay, the equations we just looked at are actually fairly complicated. Let's look at something a little more simple. Let's say I have just x plus y is equal to 3, and then x minus y is equal to 1. Once again, I have a system of equations, okay, two different equations with the same variable in them, two equations that kind of fit together here. And then as far as a solution goes, that'd be a pair of values x and y that make both these equations true. Well, this one we can kind of just eyeball. If x is equal to 2 and y is equal to 1, then 2 plus 1 would be 3. 2 minus 1 would be 1. Okay, so I'd say that's my system, my solution to the system. Okay, the two variables that make both of these true. And what we'll do today is we're going to look at a few different methods for solving system of equations and talk about when certain methods work, when they don't work. Okay, that's the idea today. So as far as methods for solving systems of equations go, one of the best ways to start is graphing. It's a great way to help visualize what's happening here. So problem 1 just says solve each system of equations by graphing. So I want to use graphs of these two lines to figure out where the x and y values meet. And for that, what I'm going to do is simply just graph these two equations. Now this is in simple form. We're thinking y equals mx plus b form, where m is the slope of the line and b is the y-intercept. So to graph this first line, y equals x plus 2, we have a y-intercept of 2, And then as far as the slope goes, when I just see this x, we can think of it as a 1x. So in other words, my rise is 1, my run is 1. We'll go up 1 over 1 the entire time. And I'll make a few points going backwards. We can connect our dots. Cheat to make it so I hit these dots. Actually, we'll make them really big. There we go. All right, so that's our first equation. Now I'll graph our second equation. Okay, y equals 3x minus 2. Y-intercept is negative 2 for this one. And the slope of 3, we can think of that as rise of 3 over run of 1. So what I'm going to do is for each point is I'm going to go up 3 over 1, up 3 over 1. Okay, I guess going the other way, we could go down 3 over 1. Okay, connect these dots. See if I can hit my points better. Yep, we got it. And I see my solution visually right here. It's going to be where these two values come together. Okay, when x is 2 and y is 4, we have our solution to this system. All right, now once we have that solution, it's pretty simple to check. Okay, a little complicated to solve for, but pretty simple to check. If I take this 4 and 2 and plug them into both these equations, so for my first one, we have 4 equals 2 plus 2. Okay, well that's just 4 equals 4, so that checks out. Second equation, we have 4 equals 3 times the 2, the x value, minus 2. Okay, so 4 is equal to 6 minus 2. 4 is equal to 4 once again. That checks out as well. Okay, so it doesn't hurt, especially when it comes to test time, to do a quick check to make sure you solved it correctly. All right, that's the idea of solving system of equations graphically. Okay, just graph the two lines and figure out where they intersect. All right, part B is a similar example. Why don't you at this point work through that one on your own? So pause the video, give part B a shot, and then hit play, and I'll run through the answer. You can use that to check your answer. All right, so let's go ahead and run through part B together here quick. I'm going to graph the two lines and figure out where they come together. First line, y equals 2x plus 4. That means I have a y-intercept of 4 and a slope of 2, or 2 over 1. So what I'll do for my y-intercept is I'll go up 2, right 1. And then for the other direction, we'll go down 2, left 1. And since I don't know where these are going to hit, I'll kind of just keep making points here. See if we can connect the dots and actually make them come together. All right, then second equation, y equals x plus 2. I feel like we just did that. Y-intercept is 2. Slope is 1. So we'll just go up 1, right 1 the entire time. And it looks like I found my intersection right there. These two equations are to come together at x equals negative 2 and y equals 0. That's going to be my solution to this system of equations. Next thing we're going to do is look at some special case solutions for system of equations. And we'll do these, I've got two of them for you. We'll do them graphically, but they'll show up with all our other methods as well. But again, graphically is a good way to visualize what's happening here. So solve the system by graphing. Let's go ahead and graph our first line, y equals 2x plus 2. So we have a y-intercept of 2. Rise over run is 2 over 1. Get some points on here, and we will connect the dots. Now for my second equation, we have y equals 2x minus 1, so that's going to have a y-intercept of negative 1. And its slope again is 2 over 1, so we'll go up 2 over 1 to keep continuously getting to that next point. And what I see on my graph here is I don't have a solution. Now, just because you don't see a solution within this window doesn't mean these graphs don't eventually come together. But in this case, I'm going to say these graphs are never going to run into each other. Since they both have the same slope, okay, we know they're parallel to each other, and parallel lines don't intersect. So this would be an example of a no solution case. And essentially that's going to happen anytime you're talking about parallel lines. We have two equations that are never going to meet. Okay, there's no x and y values that could satisfy this system of equations here. Okay, so graphically, when the lines are parallel, we know we have no solution. All right, let's take a look at the second special case. And for this one, notice my second equation isn't all set up and good to go for us to graph yet. Okay, the reason for that is if I had it all set up and good to go, we'd be able to tell right off the bat kind of what the issue is. So anytime you have a system of equations where it's not ready to graph, all you need to do is solve it for y to get it ready to graph, to get that y equals mx plus b form. So what I can do here is I can add x to both sides of this equation. That'll leave me with a 2y is equal to x plus 2. And then we can divide both sides by 2, so divide everything by 2. So that'll give me a y is equal to, we could just say 1/2 x like we have up above here. And 2 divided by 2 is a 1. And then notice what happened here. I have y equals 1/2 x plus 1. And then once again, y equals 1/2 x plus 1. I have the same equation essentially. Okay, if I want to graph these, the first equation has a y-intercept of 1, slope of 1/2, so that'll be up 1 over 2, up 1 over 2, up 1 over 2. And we'll just do the same thing going the other direction. We'll kind of eyeball it here. And then when I graph my second equation, same thing. We have a y-intercept of 1, a slope of 1/2. So what I have here is I have the same line. Okay, so there is a lot of solutions. There's actually an infinite number of places where these lines cross because it's the same line. So what I'd say in this case is infinite solutions. Okay, there's an infinite number of ordered pairs, x and y values. They're going to make this system of equations true. Okay, and again, graphically, you'll notice that's the case when you have a system that reduces down to the same line. All right, you know we have infinite solutions. All right, next up, let's look at some other methods for solving systems of equations. Okay, graphing's great, but it's not always the most practical way to go. Think of my intro problem with hybrid vehicles, okay, where our y-intercepts would be 26,000 to 28,000. I don't really feel like making a graph that looks like that, so not really practical. The first algebraic type of solution we're going to look at is going to be solving by substitution, where I have my two systems once again, and I have some steps for solving this one here. Okay, step 1 says solve one of the equations for one of the variables. Now, for step 1, I could pick either of the two equations to start with, and I could solve for either variable, x or y. But I'm going to say I want to look for the equation of the variable that's going to be easiest to solve with. In this case, that's going to be this y by itself. Okay, there's not going to be any division. I'm not going to end up with any ugly fractions. So for my step 1, I'm going to solve the second equation for the y variable. Okay, so step 1, we'll take the negative 3x plus y equals negative 4. And I want to get y by itself. So to do that, I'm going to add 3x to both sides. And that's going to leave us with y, is equal to 3x minus 4. Okay, so I have y in terms of x. I've solved that first equation for y. Okay, step 2 then is going to be to substitute the expression for that variable into the other equation. So for step 2, what I'm going to do is I'm going to take my first equation, the one that I didn't solve for the y with, the negative 2x plus 5y equals 19. And then what I want to do is I want to substitute this y expression in for the y here. So I could rewrite that as negative 2x plus 5 times, instead of y, we'll say 3x minus 4 is equal to 19. So now what I have is an equation in terms of just x. Okay, there's only one variable in this equation, the x. So now what I can do is I can solve this equation for x and figure out what the x part of my solution is. Okay, so to get the x by itself, we'll distribute across these parentheses. That'll leave us with a negative 2x plus 15x minus 20 is equal to 19. And then I can combine like terms. Negative 2x plus 15x is going to give me a 13x minus 20 is equal to 19. And as I run out of room here, we're going to add 20 to both sides. We'll just come up top here. They'll give us a 13x is equal to 39. And then divide both sides by 13. And we end up with x equals 3. So at this point I've got half of my solution. Okay, so we're halfway there. I suppose technically more than halfway, but we have half the solution. Now step 3 says substitute the solution for the first variable into either equation and solve. Okay, so here I can take this x and I can substitute it into either of these other two equations. And basically what I want to do is I want to pick the one that looks the simplest. So let's go with the bottom one. It's got the smaller numbers. Okay, the 3x plus y equals negative 4. And instead of saying 3x, I'm going to substitute this x equals 3 in. So that'll leave me with a negative 3 times 3 plus y equals negative 4. And when I make substitutions, whether it's a full expression or just a number, I like to put in parentheses. And then solving for the y, we've got a negative 9 plus y is equal to negative 4. I can then add the 9 to both sides. And we end up with y is equal to 5 for the other half of our solution. Okay, so final answer then, we could combine it and just say x equals 3, y equals 5. Okay, that's the solution to my system by substitution. Okay, so we've got those steps. We'll just walk through those again. I'll solve one equation for one of the variables. Substitute the expression for that variable into the other equation. I suppose I could say here, and solve. And then substitute the solution for the first variable into either equation and solve. Okay, part B is the same idea. Why don't you take a minute, pause the video, run through part B, and then you can hit play to check your answer. Alright, so let's run through this. Step 1, solve one of the two equations for one of the two variables. And again, it doesn't matter which one I do. I want to pick whatever's simpler. I'd say that the second equation looks simpler to me. As far as solving for an x or a y, I'd say that the x is maybe a little easier because it's already positive. But this would be pretty easy if I solve for y as well. Okay, so step 1, pick an equation. So we'll go with the x minus y equals negative 3. And solve it for one of the variables. I'm going to solve it for x, so for that we'll just add y to both sides. And that'll give us that x is equal to, we could say, y minus 3. Alright, step 2 then, we said substitute that expression into the other equation and then solve. So we'll take our 2x plus 2y equals 38. And we're going to substitute in for the x, this y minus 3. So I can write that as 2 times the quantity of y minus 3 plus 2y equals 38. All right, I now have an equation just in terms of y, so we can solve it for y. Whoops. Get that out of the way there. So I can distribute my 2 in. So we'll go 2y minus 6 plus 2y is equal to 38. And solving for y, we'll combine like terms. This is going to be a 4y minus 6 is equal to 38. I'm going to add 6 to both sides. That gives us 4y is equal to 44. And then divide both sides by 4. We end up with y is equal to 11. Okay, so there's about half my solution. We've got the y first. Now again, if you solve for x first, that's okay. You can just watch the rest of the way here and check your solution. Okay, so we'll kind of split things up here. And then part 3, I'm going to take that y solution I came up with and substitute it back into either of these two equations. Again, doesn't matter which one you use. I'd say pick the simpler one. That'd be the x minus y equals negative 3. So we'll go with the x minus y equal negative 3. We'll substitute this 11 in for the y, so we'll rewrite this as x minus that 11 we just found is equal to negative 3. And then we can solve for x. I'm going to add 11 to both sides, and that will give me that x is equal to, what's that going to be, a positive 8. Alright, so again, whether you start with the x or start with the y, we'll end up with the same solution, x equals 8, y equals 11. I want to take a look at one more substitution solution problems and show you how it can work into one of our special cases. Okay, so once again, solve one equation for one variable. Now for this one, we're already good to go. So step 1 is done. X is already equal to negative 3y plus 4. So I'm just going to use that x here. For step 2, we want to substitute that x value into the other equation. So we'll take the 6y plus 2x equals 8. And again, we're going to substitute in for x, this expression, negative 3y plus 4. So we've got 6y plus the quantity of 2 times negative 3y plus 4 is equal to 8. Then let's take a look at what happens, why this is a special case. When I distribute, I'm going to end up with a 6y, 2 times negative 3 would be minus 6y, plus 8 equals 8. Now for this one, I've got a positive 6y and a negative 6y. Those are going to cancel. And I end up with just 8 equals 8. So 8 equals 8 is a true statement. We'd say it's a tautology. And anytime you end up with an equation like this where number equals number, something that's just true regardless of the variables, we could say we have infinite solutions. Okay, meaning that no matter what value of x I picked or what value of y I picked, I could come up with the other x or y to come up with a solution for the equation. Okay, so that's what your infinite solutions case is going to look like algebraically. When you end up with a number equals itself, you know you're going to have infinite solutions. Last method we're going to show you for solving system of equations is going to be solving a system by elimination. And the reason it's good to have more than one method is each method is going to work better in different situations. So let's take a look at this system here. Now notice if I wanted to do substitution, it wouldn't matter whether I solve for the x or the y in the first equation or the second equation. I'd have to do division and end up with some kind of ugly fractions. Okay, I want to avoid that. I want to keep things simple. So what I can do instead is I can use elimination. Basically what elimination does is we add two equations together and use it to eliminate one of the variables. Notice here we have a positive 5y and a negative 5y. Okay, these two can cancel each other out. So what I'm going to do is I'm just going to add these two equations together. 2x plus 6x is an 8x. 5y minus 5y is 0y, so I'm just going to say plus 0y for now, is equal to 17 plus negative 9. That's going to give me a 8. And if I rewrite that, I end up with 8x equals 8. That's a simple equation I can just use to solve for the x. Divide both sides by 8. And we end up with just a x equals 1. And after that, I've already got half my solution here. Okay, just like with substitution then, once we have one variable, we can plug it in to solve for the other variable. So I'm going to take the original 2x plus 5y equals 17, and I'm going to substitute this x equals 1 into that equation, which makes life pretty easy. 2 times 1 plus 5y is equal to 17. So in other words, 2 plus 5y equals 17. I can now solve this equation for y. Let's subtract 2 on both sides. That's going to give me a 5y is equal to 15. And divide both sides by 5. And we end up with a y equals 3 for that part of the solution. Okay, so again, that's my elimination method. Add the equations together, okay, hopefully canceling one of the variables. Solve for the variable that's not canceled, and then substitute that back into either equation, okay, to solve for the other variable. Okay, again, in certain situations that's going to work out nice where variables will cancel. Okay, and in certain situations this is going to be easier than substitution. Let's take a look at another elimination example. And this one's not going to quite work out as easily. We're going to have an extra step to do. Okay, notice as far as canceling out variables, the x's don't match and neither do the y's. Okay, but I'm going to say the y's are close. Okay, 15 and 5, it's pretty easy to make a 5 into a 15. I just got to multiply by 3. So what I'm going to do is I'm going to rewrite this system by multiplying my entire bottom equation by 3. So I'm going to rewrite the top without changing it. So minus 2x plus 15y is equal to negative 32. And the bottom, if I multiply everything by 3, I'm going to have a 21x minus a 15y, and then is equal to 17 times 3 would be 51. Okay, now what I have is a set of variables that will cancel out. It's going to be the y's again in this case. And it could be the case where I have to multiply both the top and the bottom to get in terms of a common number. Okay, this one will be a little simpler though. So now that these will cancel, what I can do is just like in the last problem, I can add these two sets of equations together. Okay, negative 2x plus 21x is going to give me a 19x. Okay, plus 0y, suppose I don't need to show that, but we'll show how it cancels, is equal to negative 32 plus 51 would be a positive 19. Okay, so 19x is equal to 19. Divide both sides by 19 once again. And once again, we end up with x is equal to 1. All right, then again, once I have that first solution down, see if we can cram the rest in over here, pick either of the two equations, solve for the second solution. I'd say that the bottom one's definitely easier. We've got a 7x minus 5y is equal to 17. I'm going to substitute in the 1 for the 7. Okay, so 7 times 1 minus 5y equals 17. So in other words, 7 minus 5y is equal to 17. We'll subtract the 7 on both sides, get the y by itself. That'll give me a negative 5y is equal to positive 10. And then I can divide both sides by negative 5. And we end up with y is equal to a negative 2 for the other half of that solution. Okay, so that is the, we'll say, more complicated elimination case where you have to make some multiplication happen right off the bat. Okay, that's what we're going to make you practice in part C coming up here. So once again, pause this video, run through part C, and then hit play to check your answer. Make sure you're doing things correctly. All right, let's go ahead and run through part C. And this one's going to work out very similar to the example we just gave you. Okay, again, the y's are going to be the thing to look to cancel. I've got a 12y and a negative 4y. It's very easy to make that negative 4 into a 12. I'll just multiply by 3 once again. Okay, it's not always going to be times 3, but in this case it kind of works out that way. Okay, so we'll multiply the bottom equation by 3 for everything. So top equation will stay the same. Negative 2x plus 12y is equal to negative 30. Bottom equation then is going to be a 9x minus 12y is equal to 51 once again. And then once again, we'll add everything together. Okay, we can combine the x's. Negative 2x plus 9x is going to give me a 7x. We'll combine the y's, and it's not always going to be the y that cancels, but okay, it's just working out that way with these three equations. Okay, 12y minus 12y is going to be a 0y. And then negative 30 plus 51 is a 21. So we have then is 7x is equal to 21. You can divide both sides by 7. And we end up with x is equal to 3. Okay, so there's half of my solution, x equals 3. And I'll take that simpler of the two beginning equations. We'll go with the 3x minus 4y is equal to 17. Again, either one will work, but pick the one with the smaller numbers. I'm going to substitute the x I just found in. So we've got a 3 times 3 minus 4y is equal to 17. So 9 minus 4y is equal to 17. Subtract 9 on both sides. That'll give me negative 4y is equal to 8. And then divide both sides by negative 4. That'll give me y is equal to a, whoops, we need the negative here, negative 2. Let's take a look at one more elimination problem, and let's show you how we can get one of our special types of solutions through elimination. So here once again I have two sets of equations, and neither of them will cancel just by adding together. But notice here, if I multiply the top equation by a negative 2, my x's will cancel. And also my y's will cancel, which is kind of an issue here. So let's see what happens. I'm going to multiply everything on top by a negative 2. And that's going to leave me with a positive 4x minus 10y is equal to negative 24. Then we have the same negative 4x plus 10y equals 14. Now we can add. And again, what's going to happen here is the 4x and negative 4x are going to cancel out. We get a 0x. The negative 10y and 10y are going to cancel out as well, so we can play, say, plus 0y. And that's equal to negative 24 plus 14, which would be a negative 10. Okay, 0x plus 0y is just 0, so we end up with 0 is equal to negative 10. And I'm going to say we end up with something that's not true. Okay, it'll be infinite solutions if we end up with a number equals itself, but if we end up with two numbers that aren't equal, that's called a contradiction. And I'm going to say when that happens algebraically, and it can happen both through elimination or substitution, you're just going to say no solution. And again, what that means is it doesn't matter what x and y values I plug into these two equations, I'm never going to come up with something that works. All right, let's go ahead and get back to that hybrid problem. Okay, we'll use that to wrap things up here. So reminder, the regular Ford Escape sells for $26,000 and on average costs 10 cents per mile to drive. The hybrid sells for $28,000 and on average costs 8 cents per mile to drive. How many miles would you have to drive in order for both vehicles to cost the same? Well, we already came up with equations for the cost. We said that C is equal to, for the regular Escape, 26,000, all right, plus 0.10 m for miles driven. The hybrid is C is equal to 28,000 plus 0.08 cents per mile. And probably the easiest way to solve this would just be with my substitution method. Okay, both these equations are already solved for C. So what I can do is I can just set these two equal to each other. I can think about plugging in for this C, the 26,000 plus 10.1 miles. So let's go ahead and do that. So we'll say that 26,000 plus 0.10 m is equal to the 28,000 plus 0.08 m. I now have an equation that I can solve for m, and I'm going to do that by getting all the m's on one side. I'm going to subtract a 0.08 m from both sides of this equation. That's going to cancel out the m's on the right, leave me with just the 26,000 plus a 0.02 m on the left is equal to 28,000. Then I can subtract the 26,000s from both sides to get the m alone on the left. Big numbers, but the math's actually pretty simple. Those will cancel. We end up with a 0.02 m is equal to 2,000. It's my difference in their initial price. And then if I finish that off by dividing both sides by the 0.02, that's going to leave me with just the m on the left. And on the right we have 100,000. All right, that's my solution here. We want to know how many miles would you have to drive in order for both vehicles to cost the same. Okay, well that's going to be after 100,000 miles. That's when their prices will equal. Okay, beyond that, the hybrid will be cheaper to drive. As far as years go, typically drivers are somewhere around 20,000 miles driven per year. Okay, probably a little less than that. But in other words, after 5 years, that's when that hybrid vehicle is going to start paying off. Okay, so that's it for our system of equations lesson review. Finish it up with a nice real-world problem where, hey, in a few years you might have to make a decision, something like this. Okay, start working on the Math Excel assignment. That's just going to give you more reps for this stuff. That's going to allow you to kind of get some help as you go and check answers as you go. And then you can move on from there into the practice test and the test.